Here we see three Maclaurin series. The Maclaurin series for e to the x, the Maclaurin series for cosine of x, and finally for sine of x. These ones have shown up a whole lot, and we've probably got a lot of practice with them at this point. I want to show you a neat connection between all three of them. But to do so, we first need to review a little bit about the complex numbers, and especially the imaginary unit I. I always like to think about I as a number so that when you square it, you get -1. And of course, you can also think about I as the square root of -1. So let's just start with I, and very boring. I'm gonna write I equals I, and it looks funny because of course it does. But now I want to square I, right? And well, I squared would be I times I. Well, that's -1, right? We have that up here in the definition. Now I want to think about I cubed, and I want to keep increasing the power of x. But what I realize I can do is multiply both sides of the equation above by I to get the next one. I times I squared is I cubed, and so that has to be equal to -I. Well, let's just keep going in that fashion. So I to the fourth would be -I squared, minus a -1 is just 1, and so I to the fifth becomes the same as I. And I've kind of looped back to the beginning, and I'm going to see these kind of just loop around again, those familiar values. And what I have established here is a pattern that continues all the way down. It also tells me that every multiple of 4, I'm going to get 1. So I to the 12th has to be 1. I to the 100th has to be 1. And now I want to consider e to the I theta as a power series, as a Maclaurin series. We know that e to the x converges absolutely for all values of x. And if I replace it with a continuous function, and even with that complex number in there, that is a continuous function, it'll converge over the same interval, having replaced x with I theta. Well, that converges absolutely everywhere, so this one will too. So all I have to do now is do the replacement. Everywhere there is an x, I'm supposed to replace it with an I theta. And so if I just do that as, I don't know, I guess naively as possible, right now it would look something like this. And now I could think about raising I to those powers, right? And well, I squared's -1, so the i's go away, and I just get theta squared over 2 factorial. I cubed's -I. Get that theta cubed and a 3 factorial still on the bottom. I to the fifth is a positive I. All right, and let's just do one more term, even though I didn't actually even write out another term there. Of course, now I realize I actually skipped a power here. That's embarrassing. Let's fix that. This should have been a 4 and a 4 factorial. And so let's back that up. I to the fourth is 1. That should be a theta to the fourth over 4 factorial. All right, now that I to the fifth, that would be that next term I was talking about, would be hanging out right there. Well, I to the fifth is I, theta to the fifth over 5 factorial. And I think we can see a pattern, and this one's kind of cool. Positive, positive, negative, negative, positive, positive. And it'll keep doing that all the way down. And in fact, I think anyone who saw this could now replicate it. All right, well, this series converges absolutely for all values of theta to e to the I theta. And that's important because we have a theorem that says if we have a series that converges absolutely over that interval, we can rearrange the terms and the series will still converge to the same thing it used to. And so what I want to do is now pick out all of the terms that would not have an I in them. And what I see is an alternating series that seems really familiar. And let's see, now I want to write down all of the terms, right, that have an I in them. I theta minus I theta cubed over 3 factorial plus I theta to the fifth over 5 factorial. All right, well, I see those two things, and now I can actually imagine factoring an I out of that second set of parentheses. And so let's see. I have that would be equal to 1 minus theta squared over 2 factorial plus theta to the fourth over 4 factorial. And let's see, I'm going to add in a term just for the heck of it because we know what it's going to be. All right, now plus I times theta minus theta cubed over 3 factorial plus theta to the 5th over 5 factorial. And you know what, let's write down one more term just because we did on the other one. All right, well now I have two things being added together, and if I look all the way back at the beginning and I compare, what I have here in theta is the Maclaurin series for cosine. This one converges to cosine of x plus I times, we'll look at this one, and I have the Maclaurin series for sine in the variable theta. So, what we can now conclude without any hesitation is that e to the I theta is equal to cosine theta plus I sine theta. And that is called Euler's formula, named for mathematician Leonhard Euler. All right, well, let's look at Euler's formula just for a moment. E to the I theta equals cosine theta plus I sine theta. The Maclaurin series from which this came converged absolutely everywhere, so this equation holds for all values of theta. So let's imagine what happens when we plug in a pi. All right, well, the cosine of pi is -1 and the sine of pi is 0. So e to the I pi is equal to -1. And if we add a 1 to both sides, we get a beautiful statement. E to the I pi plus 1 is equal to 0. And that gets called Euler's identity. And it is one of the most beautiful statements in the whole of mathematics. And one of the reasons I think that's true, and some other folks think that's true too, is because it relates 5 of the most important constants in all of mathematics in one equation. E raised to the I pi plus 1 is equal to 0. We have the additive identity, the multiplicative identity, our constant that comes from the ratio of a circle's circumference to its diameter, the imaginary unit, and then Euler's number, E. And that is a beautiful statement.